Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we were discussing about the various memory management techniques. We have seen up to now that the fixed partitioning and the dynamic partitioning can be used for the contiguous allocations. Both of these suffer with the kind of the fragmentation, and the defragmentation schemes, for example, the compaction is required to deal with the external fragmentation. However, the internal fragmentation cannot be removed. We have also seen the segmentation scheme, and the segmentation scheme was creating a user view of the program, and the different segments are created for a process, and those processes get accommodated in the different portion of the main memory. It means this was the non-contiguous allocation scheme. This non-contiguous allocation scheme segmentation also suffers from the fragmentations. This suffers from the external fragmentation, and the only solution for that again will be to do some kind of the compaction. So, compaction is a costly scheme, and the CPU gets busy for doing the compaction, and it does not do the execution of the programs during the process of the compaction. So, we actually do not go for these schemes usually, because it is a very costly scheme. We should go for some schemes which does not fall into any kind of the fragmentation. So, the paging scheme is there that divides the pages into the equal size chunks, and the main memory is also divided into the equal size chunks, and the pages do get adjusted into the frames directly. So, we have discussed the paging in detail in the previous terms, and we have also discussed about some of the numericals, how to solve the numericals related to the paging. So, in today's turn we will discuss about the optimal page size, we will discuss about the translation look-aside buffer, and we will also see that why the memory protection is required in the paging and how the protection is done. So, once again the start of the lecture would be from the logical and the physical address. This is the major thing whenever we are translating the address from the CPU referred address to the actual address, that is known as the physical address. So, any address referred by the CPU is known as the logical address, and the logical address considers that the addresses are starting from 0 for any of the process. When these processes get accommodated into the main memory, the address occupied by the process will be the physical address, and CPU generated logical address will be converted to the physical address with the help of a unit known as the memory management unit of the operating system. Set of all the addresses generated by the CPU is known as the logical address space, and set of all addresses possible in the RAM will be the physical address space. Now, we already have discussed a bit about the paging scheme. The pages are equal size chunks of the process, and the frames are equal size chunks of the main memory. The pages do get adjusted in the frames directly and leaving no space free in between. We maintain a segment table also in between, just to keep a track of which page has gone to which portion of the memory or which frame of the memory. So, a page table is required. This page table contains the frame number entry for all the pages. Let us say this is the first row of the page table. So, this will contain the frame number corresponding to page number 0. Similarly, the second row will contain the frame number corresponding to the page number 1, and the third row will contain the frame number corresponding to page number 2, and so on and so forth. So, the total number of rows in the page table will be total number of entries in the page table will be same as the number of pages. Okay. Now, CPU refers to the logical address. Logical address is divided into the two components, page number and offset. Here the offset is same for the physical address as well. The page number referred, we refer to the page table for this, we get a frame number from here, and this frame number is provided for the physical address. So, the concatenation of frame number and offset gives us the actual address or the physical address of the referred instruction in the main memory. Fine. This is how the address translation is done. So, for the address translation we require a page table in between. Now, let us solve a numerical. This is saying that we are doing the single level paging scheme. just ignore this statement because we have not discussed about multi-level paging. The virtual address space is 4 MB. So, virtual address or logical address space meaning the same thing. 4 MB means in the logical address we will have 4 MB means 4 into 2 raised to the power 20 bytes. So, this is 2 raised to the power 22. So, 22 bits will be there in the logical address and page size is 4 kilobyte. So, the page size is 4 kilobyte, it means 2 raised to the power 12 bytes. So, 12 bits will be there in the offset field of logical address. Rest of the fields will be or rest of the bits will be telling you the page number. So, the page number bit contains 10. So, total number of pages will be 2 raised to the power 10. Now, the physical address will have two components, one will be the frame number and the other one will be the offset. Since the offset of the logical address and the physical address remain the same, so you can say that the physical address has the offset bit as 12. We do not know the frame number bit, but rest of the information is given later. So, what is the entire page table, what is the maximum page tables entry size possible such that the entire page table fits well in one page. It means the page table size is given, page table size is equal to the size of the page. The entire page table gets fitted into one frame, it means the page table size will be same as that of the one page or one frame. So, what is this page table, what is the size of a page? Page size is 12. So, page table size is 2 raised to the power 12 bytes, it means 4 MB, 4 KB sorry. So, 4 kilobyte is the size of page table. Okay. The page table contains the entry for each of the page, and how many pages are there? 2 raised to the power 10. So, 2 raised to the power 10 page entries will be there and each of the entry will be, we will be containing the frame numbers. So, we do not know what is the frame number bit. So, let us say frame number bit referred to as f. So, 2 raised to the power 10 into f, this is equals to 2 raised to the power 12, it means f is equals to 2 bytes, 4 bytes sorry, and 4 byte can be said to as 32 bits. It means the entry in the page table requires 32 bits, per entry we require 32 bits, and if we fit 32 here in the frame number of the physical address, we have a physical address size as 2 raised to the power 44. Okay, this is very big, it is something like 16 terabyte. So, 16 terabyte is the size of your physical address or the RAM. So, this is how we solve the numericals like this. Now, let us have a concept. Let us say we have a process of size 90 bytes. Okay, let us say not 90, but let us say it is 95. Okay, let us say 95 bytes is the size of a process. Let us say we are going to divide it into the pages of size 30 bytes. So, there will be total 4 pages, one page will be containing 30, another will be containing 30, another one will be containing 30, and the last one will be containing only 5 bytes. Okay, last one will be containing only 5 bytes. Okay. Now, when this process will be accommodated in the main memory, there is no issue with the other pages, but there is an issue with the last page. When the last page gets adjusted in the frame, since the frame size will also be of 30 bytes, there will be a wastage of 25 bytes. So, this is actually the fragmentation, some kind of the fragmentation is happening here. So, whenever you will store the last page of your process, there will certainly be some fragmentation, and this fragmentation cannot be resolved. This will be the sheer wastage of the memory. So, this will be the internal fragmentation. Now, suppose we are not dividing this page in the 30 bytes, but we are going to divide it into the 20 bytes pages. So, when it is divided into the 20 bytes pages, so 20, 20, 20, 20 and last page will be of 15 bytes. Frame size will also be of 20 bytes. So, if you put the last page somewhere in the main memory, there will again be a wastage of 5 bytes, although it is very less than the 25 bytes, but yes, there will be a wastage. Now, if you again reduce the size of the page, let us say you divide it in the 10 bytes pages. So, 10 bytes pages will be created and the last page will be of size 5. Okay. When 5 byte page will be adjusted in the main memory in the frame size of 10 bytes, so once again there will be a wastage of 5 byte. Okay. Now, what is happening here, that in the first case or in the first division, when we have created a page of 30 bytes, you require only 4 entry in the page table per page entry. So, there are 4 pages, so 4 entries. When you have divided it into the 20 bytes, you require 5 entries in the page table. When you divide that in the 10 byte size, then you require 10 entries. So, as you increase the number of the pages, your page table size will be increasing. And similarly, when you are actually decreasing the size of the page, then the fragmentation becomes smaller. So, the page table size is increasing and the fragmentation is getting down. Okay. And when you are increasing the once again, let us take the beginning, go to the beginning. When the page size is large, the fragmentation is large, but the page table entries are less. So, both the things means the fragmentation because of the last page and the segment table, both are the wastage of space for us. So, we should decide that which page size is actually perfect. So, for doing so, let us do some computations. So, let us say a process is of size, let us say S, and the page is of size P. Okay. Page is of size P. So, the total number of pages will be, now let us do it like this, page process size, let us say is equals to S. Let us say the page size that you have selected is P, number of pages will be S upon P. Fine. The number of entries in the page table will be S by P. Okay. Number of entries in the page table will be S by P. Let us say each of the entry requires E bytes. Let us say each of the entry requires E bytes. On an average, it is considered that the half of the page size will be the wastage of space in the last, because of the last page. It means the total fragmentation because of the last page will be, let us say, half of the page size. So, that will be P by 2. So, S by P into E is the size of the page table, and the memory wastage because of the last page will be P by 2. Let us say the P by 2 is the size of last page. So, when it is accommodated into the frame has a size P. So, P by 2 will be the wastage of space. Now, segment table is stored in the main memory. When last page is stored in the main memory, then there will be a wastage of P by 2 space. So, entirely this will be the total wastage of space. Okay. Total wastage of space will be this. Let us say this is W. We are deciding that what should be the optimal page size. Optimal means maximum or minimum, whatever you say. So, for this we need the derivative of this. So, when you take the derivative of this with respect to the page size, this will be minus S upon P square into E plus 1 by 2. So, for minimum or minima or maxima, this value should be equals to 0. So, S by P square into E is equals to half, or you can say that P square is equals to 2 into S into E, or you can say that P is equals to under root 2 S E. So, this is the optimal page size that we should select. So, based on this, Let us solve some of the numericals. We have been given that the page size is 4 kilobyte, the number of bytes required per table entry in the page table is 8 bytes. So, what is the optimal page size? So, we know that P is equals to under root 2 S into E. So, 2 into S is 4 kilobyte, let us represent it in the bytes. So, this will be 2 raised to the power 12, and then E is referring to the number of bytes per entry. So, that is equals to 8. So, 8 is again represented in powers of 2, this is 2 raised to the power 8. So, together it is 12 plus 8 into 2, sorry 8 will be 2 raised to the power 3, not 2 raised to the power 8, 2 raised to the power 3. So, together this is 2 raised to the power 16. So, this will be 2 raised to the power 8. So, it means 256 bytes should be the optimal page size. Similarly, we can solve the next numerical as well. This one, this is saying that the size of the process is 16 MB and this entry requires, or per entry in the page table requires 2 bytes. So, what is the optimal page size? So, P is equals to under root 2 SE, S is 16 MB, when represented in the power of 2, this will be 2 raised to the power 24, and each entry requires 2 bytes, so multiplied with 2. So, together it is 2 raised to the power 26, means 2 raised to the power 13, means 8 kilobyte. So, the optimal page size in this case is 8 kilobyte. Similarly, we can solve the last one. It is saying that the size of the process is 256 gigabyte and each entry requires 32 bytes. So, page size, optimal page size will be under root 2 SE. So, this is equals to 2 into size of the page is 256 GB, means a big quantity. Let us do it outside. So, 256 GB means 2 raised to the power 8 into 2 raised to the power 10 MB into 2 raised to the power n KB into 2 raised to the power 10 bytes. So, this is 2 raised to the power 38. Each table entry requires 32 bytes, 32 bytes means 2 raised to the power 5. So, together this is 2 raised to the power 44, it means 2 raised to the power 22 should be the optimal page size. When represented in the bytes, it will be, this is the bytes, 4 megabyte is the optimal page size. Now, whenever we are maintaining the information about the pages in the page table, for accommodating the new processes in the main memory, we should also maintain the free frames list. So, there is a kind of the data structure which requires the information about all the free frames in the system or free frames in the main memory. So, let us say this with an example, that we have the free frame list containing 14, 13, 18, 20 and 15, and a new process is coming which requires the 4 spaces or 4 pages. So, 0, 1, 2, 3 is the page number of this process. So, the first frame allocated to the page number 0 will be 14. So, page number 0 is going in frame number 14. Similarly, next page 13, next page number 1 will be going in frame number 13, and then next page, page number 2 will be going in the frame number 18. Similarly, 20 is the next frame free. So, page number 3 will go in the 20. Accordingly, we need to maintain the page table. You can see that here we have the new process page table, where 0 page goes to 14 frame, 1 page goes to 13, 2 goes to 18, 3 goes to 20. So, this is the page table maintained. So, we need to maintain the free frame list for accommodation of the new processes. So, you can consider that the free frame is some kind of the linked list, and from the linked list you delete from the beginning and allocate it to the processes. Okay. So, the free frame is the data structure that you need to maintain. So, you are maintaining the page table, you are maintaining the free frame list also. So, there are 2 overheads involved with the page tables. or paging scheme, we have two overheads involved. Now, you see whenever the page table is referred, with the example or with the numerical, we have seen that the page table will be stored in the main memory. Obviously, page table will be stored in the main memory, and we will be maintaining this information for each of the process. So, when you refer to any of the bytes or any of the instruction, or when CPU refers to any of the instruction, it requires two memory references. One, it requires the page table, and then it requires the actual storage of the byte in the main memory. So, both the things are required there. Since both the things are required, it means there are two memory references which may go slow or which may slow down our system. So, we need to maintain some method, or we need to find out some method by which I can speed up the access of the instruction from the system. Fine. So, there is an example of the translation look-aside buffer. This translation look-aside buffer is actually known as the associative memory, or associative memory is a concept wherein you can do the parallel search. So, when the parallel search are allowed, then you say that you have the associative memory. So, we are maintaining a hardware known as the TLAB, and what will be the storage in the TLAB or the associative memory? The page number and then the frame number. Let us say we are dealing with a state, we are dealing with the page, and the page size is, let us say, 64 bytes. It means 64 bytes in the sequence will be in one page. So, when CPU will be referring to the instruction number 0 of this page, obviously it will be referring to the instruction number 1 of this page next, instruction number 2 of this page next, instruction number 3 of this page next, and so on and so forth. It means CPU will be referring to the same page number for 64 times. So, it means if we refer to the page table again and again for the same page number for finding out the frame number, so that is actually the overhead for us. So, better to store the frame number found for the page number in some faster memory, and whenever CPU refers to that, just go to that entry in the faster or the faster lookup table and find out the frame number from there. So, this associative memory or the TLAB is storing a page number and corresponding frame numbers, since same page can be referred again and again. So, why to go for referring to the page table again and again, because we will have to refer to the main memory. So, this TLAB is some kind of the cache, or it is a faster memory. What we are going to store? We are going to store a page number and corresponding frame number for this. So, what will be the method of the search? CPU refers to the logical address divided into the two part, page number and offset. First, go for searching the page number in the TLAB. Now, TLAB is doing the parallel search in all its entry to find out if the page number exists or not. If the page number exists, then corresponding frame number is found. So, this is called the TLAB hit. If the page number is found in the TLAB, we are saying that this is TLAB hit. So, from here we have got a frame number, but if TLAB miss is there, it means the page number is not found in the TLAB. So, go to the page table stored in the main memory, find out the frame number. So, frame number can be found from either the page table or it can be found from the TLAB. So, we would like that it should be found somewhere in the TLAB, but it cannot happen always. Okay, we have found a frame number, we have the offset in the logical address, together with this we have the address of the instruction in the main memory. Now, what is happening here? That let us say TTLAB is referring to the time of access in the TLAB, and TM is referring to access of instruction in the access of instruction from the main memory. Then the effective access time T effective will be what? So, that is what we have to find. Now, here H is referring to the hit. It means if we found the page number in the TLAB, it is a hit. If we did not find, it is a miss. So, let us say 70% of the time it is found in the TLAB. So, hit will be 0.7 and 30% is not found. So, miss will be 0.3. Okay, so, this is taken in the fraction. So, if hit is H, miss will be 1 minus H. Okay. So, what will be the T effective? If hit, then search, you have performed the search in the TLAB, and then you got a frame number, go to the main memory and access the instruction. So, you have referred to the main memory as well. Now, if you did not find it here in the TLAB, so then you will go to, first you have searched in the TLAB, so TLAB search was involved, time was required, it has failed, so you go to the segment to the page table. For referring to the page table, you go to memory. Okay, so TM time is required. Now, after that you will get a frame number, go to the main memory at that location, it means again a TM time is required for referring to that instruction. So, when hit, you will only go for finding out the instruction, but when it is a miss, you will go to first find out the segment table entry in that is also there in the main memory, and then for the instruction as well. So, two memory references are required here. So, this is what written here, H plus T TLAB plus TM, or 1 minus H plus this one. Okay. So, this can also be referred to written as T TLAB plus TM plus 1 minus H T TLAB plus 2 into TM. Okay. So, here are the numericals that you can solve for finding out the effective memory access time. Now, for this entry, let us say you have to find out the T effective. So, what will be the T effective? Hit is 80%. So, 0.8 into TLAB requires 20 millisecond, memory access requires 100. When it is a miss, means 0.2, you require to search TLAB first, then go to memory for page table entry, and then go to memory for the instruction. So, this is 96 plus 44, 220 into 0.2, 44. So, this is 140 nanosecond, that is the effective access time. You can note down other numericals, and there are missing parameters that you can find out with the help of the formula. Now, this is the another representation of this effective memory access time. Let us say we are referring to the miss first. So, when it is a miss, let us say X is referring to the miss, then I will be going to TLAB, page table, and then memory for accessing the instruction. If there is a hit, so hit will be represented by 1 minus X. So, TLAB and then going for the instruction in the memory. So, when you expand this, you find this formula. Okay. When compared it with the equation of the line, that is y equals to mx plus c. So, this is mx and this is c. So, this is the straight line, okay, and this is t plus m, time for TLAB plus time for memory. This is the TLAB miss. As the miss increases, the effective access time also increases, but the effective access time cannot go below t plus m. So, this is what it is telling, effective access time cannot go below t plus m. Now, in the memory we provide an additional bit that is known as the prediction bit. So, along with the entry of the frame number in the page table, we store the valid or invalid bit also. The concept of the valid and the invalid bit is that whether my page is present in the main memory or not. It is not essential that my page or referred page will be there in the main memory always. It may be there, it may not be there. Okay. So, if it is there, the valid bit will be 1. If it is not there, the valid bit will be 0. For example, I am referring to the page number 7 and my page is not present. So, the valid invalid bit will be containing 0, meaning that the entry is not present in the main memory, or the page is not present in the any main memory frame. Okay. If my page is present, let us say the 4 number page is present. So, here will be 9 and valid bit will be 1, meaning that the page is present in 9 number frame. So, we will discuss more about the memory protection on the next turn. We will deal with some of the numericals also related to the memory protection. So, this is the reference for today's lecture, the operating system concepts by Silverchair and Galvin. Thank you.